Hi, and welcome to Allen High School. We are a pre-AP chemistry class beginning our studies of acids and bases. We've had already a brief introduction into the three theories of acids and bases: Arrhenius, the Bronsted-Lowry, and it's the Bronsted-Lowry upon which we're going to land for the rest of the unit. And then looking simply at the definition of Lewis acid and bases. And the goal of that is for you to realize that we do have slightly different models of acids and bases, especially the Lewis and the Bronsted-Lowry, that serve different purposes. Organic chemistry, for example, uses this concept of Lewis acids and bases extensively. And so they're very, very valuable. We're going to land on the Bronsted-Lowry as an introduction. So the rest of this unit will be focusing on the Bronsted-Lowry, in which an acid is a donator or donates an H+, a proton. And remember, another way of discussing that, and actually a more accurate way of discussing that, is as H3O+. And bases are substances that, whoops, don't know where my mind was going there, except that H+. So it's kind of like a gift. A gift needs both a giver and an acceptor, or it's not a gift. So you're not going to have an acid unless there's a base present, and vice versa. All right. Now, acids and bases don't always take the normal format. They can look a little different. And so we want to start talking about what acids look like, what bases look like, what does the reaction look like, how would we describe it, what are the patterns, what are the trends that we are looking for as we look for something that is losing an H+ and something that is gaining an H+. How do we identify, how do we zero in on the behavior that we're dealing with? And when we have an acid, when it loses an H+, it forms a partner. And that partner is called a conjugate. Okay, so acids have conjugate bases. So once an acid does what acids do best, the remaining is called its conjugate base. So if I take the acid HNO3, once acids do what acids do best, which is donate that H+, I have that NO3 remaining. So this is my acid, and this is its conjugate base. Do you notice the only difference is the H, and if you're neutral, and if it's neutral and it's lost a plus charge, it's now negative. Okay. Now, we typically discuss these as the product, and very often they're going to be the charged species. Now, bases have conjugate acids as their partners, and the conjugate acid is what remains after bases do what bases do best, which is to accept. So let me put kind of a wacky little base here. Our weak bases that we're going to talk about center on nitrogen. And so when that nitrogen accepts a proton, and you must put water in there, I'm going to add an H to that. So instead of NH, I'm going to have NH2 and a plus charge. So you add an H and a plus charge, and that leaves the water deficient an H and a plus. So this was my base, and this is the conjugate acid. Notice that bases and conjugate acid deviate, or they are differentiated only by one H and a plus sign. So instead of NH, it's NH2, and it was neutral, I added a positive. Okay, so that's the definition. And an acid, remember, is partnered with a conjugate base. A base is going to be partnered with a conjugate acid. Now, this is tricky. These can be very tricky to identify. So let's take a look at how we can do this. If we go from here to here, we lost an H and a plus. That will always be the only difference between the partners, is an H and a plus charge. Well, since it was the loss of an H and a plus, HCl must have been an acid. Cl minus must be its conjugate base. Okay? Now, if I go between the other two species that differ only in an H and a plus, this was a gain of that H and a plus. You're looking for things that differ only by an H and a plus. I've said that so many times you're probably going to get sick of it. Gaining an H and a plus is a base. So water acted as a base, H3O plus. Remember, that's called the hydronium ion. Is called its conjugate or paired acid. Okay, so you need to know that word, conjugate acid. So let's take a look at a few more examples. Now, we're looking for species that between reactants and products differ only by either adding an H or taking away an H. So if I go from PO43 minus to HPO4, that's a gain of an H and a plus. While bases gain H's and pluses, that must mean that this is its conjugate acid. Now, take a look at what it does in the reverse. Do you notice in the reverse direction, the conjugate loses an H and a plus? It's an acid. A conjugate acid's an acid, and acids lose H and a plus. So that's why we call it paired. In the forward direction, it's a base. Its partner acts as an acid in the reverse direction. Now let's take a look at this next one. Again, we have water. The difference between these two species is only that H and a plus, and in this case, water gained an H and a plus charge. Excuse me, that was a little elderly moment there, kiddos. Sorry about that. It lost, my bad, an H and a plus. So you notice that water acted as an acid, which means this is its conjugate base. Again, notice as we swing around, if we were doing the reverse, what does the conjugate base act as? A base. Okay, so do you see that in the forward direction they're acting as appropriately acids and bases? And in the reverse, the conjugates act as acids and bases as they are named. Okay, I want you to notice something else that's interesting. Do you notice up here water acted as a base and here water acted as an acid? Something to think about. Let's go on. Sulfuric, HSO4 minus. Okay, well, let's look over here. Which species differs only by an H and a plus? And it's this one. So as I go from here to here, those are partnered. And I know they're partnered because they differ in an H and a plus. And in fact, it gained an H and a plus charge. Things that gain an H and a plus charge act as a base. Therefore, this must be a conjugate acid. Okay. Now let's take a look at this. As we go from here to here, that's a loss of an H and a plus. Notice instead of 3 H's, we have 2. Instead of neutral, it's -1. Okay, right? Because if you lose a positive charge, you're now down into the negatives. And that makes this an acid, and this is its conjugate base. Do you notice we always have an acid and a base together? It's like you got to have the gift giver and the gift taker. Okay? So let's take a look at this one. These are the two that differ only in the H and a plus. So that's a loss of an H and a plus. Things that lose H and pluses are acids. This must be its conjugate base. As we go from here to here. Now this is one of those nitrogen ones. Do you notice we put the H and the plus over clustered by the nitrogen? It's the nitrogen that accepts that H and the plus in the molecule. So this was plus an H and a plus charge. And so since you add proton, this must be a base. Its partner is a conjugate acid. Okay? So I hope you're kind of getting the hang of some of these. Let's go on and see if we can do a few more. of these reactions here. Now, here we have a list of bases, and we want to know their conjugate acids. Well, in order to find the conjugate, you do what bases do best. You add an H and a plus charge. So instead of NH3, I have NH4. Instead of neutral, I have a positive charge. So that would be its conjugate acid. We did this one earlier. I'll do it again just so you have it complete in your notes. Instead of NH, remember we put it on the nitrogen, we have NH2, and we added a plus sign. The sulfate ion. The sulfate ion is SO4 2-. Now we're always going to be dealing with these one at a time. So I'm only going to add one H, and if I have -2 plus 1, I now have just a -1 instead of the -2. Water. Water's H2O. If it's acting as a base, I'm going to add an H, so now I have 3 instead of 2. It was neutral. 0 plus 1 is +1. Okay. Now I'm going to tell you right off the bat, some of these are not realistic. We're doing them just as examples to help you understand the process. One of the reactions below honestly doesn't go. And this is one of those things that's not likely to go, but it gives you the concept. It does a little bit, but not very much. What do acids do best? To go from an acid to its pair, acids do best is lose an H and a plus. So instead of 3 H's, I have 2. Instead of 0, I have a negative charge. Okay, I went down. I lost a positive from 0. To go from here to here, I'm going to lose an H. So instead of 2 of them, I've got 1 of them. And instead of a -1, I've gone down more. I've lost an H plus. And you know, if you need to draw yourself a little number line that gaining H plus goes in this direction, in the positive direction, losing an H plus makes whatever the charge is become 1 more negative. Okay, so it's going to go 1 more negative, so it's going to be -2, or more appropriately 2 negative. Okay? So if you need that kind of a little number line, it becomes more positive when it gains, it becomes more negative when it loses. All right. Nitric acid, ic came from 8, nitrates NO3, so I have HNO3. I need to lose that H and a plus charge. So I was at 0. If I'm losing an H plus, I'm going to become more negative. So it goes back to nitrate. Now water. Again, notice water can act as an acid and a base. Interesting. This time it's acting as an acid. Now, I'll tell you, you might be tempted. In fact, I'll erase. You might be tempted to say, okay, I'm going to lose an H and a plus sign. So instead of 2 H's, I have 1 H and a negative. Okay, but as we say in chemistry, there's no hose in chemistry except for holmium. It's hydroxide. We write that as OH minus, and you want to do that because that's a key component in basic solutions. All right, so, all right, that gives us hopefully a good idea of how to do these. I think I'm just going to skip this chart because I think you have the idea. If you don't, ask me to do this chart in class and I'll work it out in class. So until then, this is signing off.